Hi class. So this is the first video on projectile motion. And so far we've done problems with free fall where we did one of two things. We either dropped an object off of a tall building and we were able to determine things like how long it takes to reach the ground, or we kicked or shot an object straight up in the air and we were able to figure out how much time the object spent in the air, how high it went, those kinds of things. So that's what we've done thus far. What we're going to do now with projectile motion is we're going to add a sideways aspect to that motion as well. So the objects will go up and come back down to the ground as usual, but they won't just go straight up and come back down. They're going to also have a certain sideways motion. Now what's making it come back down again? It's still gravity that's pulling it back down to the earth. The only difference is that it now also moves horizontally. It moves in the sideways direction. All right, so let's talk about, let's just look at our total velocity and fire that cannonball again. So the velocity is represented by this green arrow here, and you can see that the direction of the velocity is changing all the time throughout the motion. You can see the velocity is kind of pointing upward. Now the velocity is pointing sideways. Now the velocity is pointing downward for the most part, down at an angle. And that is the instantaneous velocity at each moment in time. But when we analyze the projectile motion, we're not going to be looking at the total velocity. We're going to be looking at the components of the velocity. So what is that going to look like? That's going to look more like this. So you can see we see two little arrows here. These are two velocity arrows. One's pointing straight up and down, that's vertically, and one's pointing sideways. So let's look at that again. So at the beginning, when it first is fired out of the cannon, and I know the cannon looks very big here, but the moment it leaves here, you're considering it as having left the cannon. So it's got this upward velocity, but it also has this sideways velocity. Right? We're not shooting it straight up, so it also has a little bit of a sideways velocity. But let's look at what happens to these two velocities. And let's focus on the upward velocity, the vertical velocity first. And you can see that there is a large upward velocity. And as you probably are anticipating, that is going to decrease due to gravity. So a little further along, that upward velocity has decreased quite significantly. At the highest point, that upward velocity has now all disappeared. And now we have an opposite or downward velocity, and it gets larger and larger and larger as it comes back down to the ground. And that is all due to the acceleration due to gravity. Okay, so let's just try that again. So we have just like we had when we kicked an object up in the air, it had a large positive velocity that decreased to zero, and then it increased, the velocity increased as it returned to the ground. So that component of the velocity is the exact same as we were doing when we shot an object straight up in the air. Okay, that velocity starts out positive, it goes to zero, and then it increases on the way back down to the ground. Let's just look at that one last time. So it increases, the up and down velocity goes to zero, now the up and down velocity, or the vertical velocity, increases. All right, so we're used to that from our free fall work thus far. What's different now is that the object also has a sideways velocity. So let's focus on the sideways velocity right now. So we have this small sideways velocity here. And what you'll notice is the whole time it's moving, that sideways velocity does not change at all. So that sideways velocity is consistent the whole time the object is in the air. Look at this horizontal arrow, this x-axis arrow, this sideways arrow. Okay, that does not change the whole time it's in the air. And the reason for that is because gravity only changes the velocity in the vertical direction. Gravity does not change the velocity in the horizontal direction. And in the absence of any force acting in the horizontal direction, the velocity stays the same. So there's nothing that is changing the velocity in the x direction. And so the velocity stays the same the whole time. This sideways velocity arrow stays the same. Okay? And the total velocity really is the sum of those two velocities, the vertical and the horizontal. But the important point is that the horizontal velocity stays the same the whole time the object is in the air. And when we were doing free fall, we had two kinds of problems. One where the object was kicked straight upward or thrown straight upward, and then it would come back down again. And the other problem was when we dropped something off of a tall building. So the other problem that we've been solving would be something like this, where we just drop a ball straight down. Right? We drop a ball off of a tall building. And when we drop a ball off of a tall building, the initial velocity is 0, right? It was dropped, and it speeds up on its way down to the ground, and we can compute things like how tall was the building if we're given the time that it takes to reach the ground, or the final velocity, or something like that. Or vice versa, if we know the height of the building, we could determine the time it will take to reach the ground, or the final velocity that it will have when it reaches the ground. So we're used to solving those kind of problems in free fall. Now the difference is going to be it's going to have some sideways velocity. And so the object is going to still fall down to the ground. It's just going to also be moving sideways. And again, let's look at this. So at the very, very beginning, right at the very beginning, even before this, right when it first was launched, I know this cannon, it looks like it shouldn't have come out of the cannon yet, based on the way the cannon is drawn, but we're pretending there's a very, very small cannon over here. So the cannonball has already come out of the cannon. And as soon as it comes out of the cannon, it starts to accelerate in the downward direction. So we start to get some downward velocity, and a little while longer, that downward velocity gets larger, and a little while longer, that downward velocity gets larger, and that downward velocity keeps getting larger because gravity is accelerating it in that direction. But let's look at the horizontal component. So the horizontal component, so here we have a sideways velocity of a certain size. And if we look at that, the whole time in the air, this sideways velocity doesn't get any larger or any smaller. The horizontal velocity stays constant. Okay, so the vertical velocity changes due to gravity. The horizontal velocity, the whole time it's in the air, does not change at all. Okay, so that's the basic idea of free fall. The other thing you should know in this problem is, well, what is the initial velocity at the beginning, right when the ball is right here? Let me see if I can stop it almost immediately. Okay, so, sorry, here we go. Oops, let me clear that, start that one more time. I wanted to get it as close as possible up here. One more time. Okay, that's about as close as possible. So when it's originally fired, it only has a sideways velocity. It only has an x-axis velocity. It doesn't have any y-axis velocity. It doesn't have any vertical velocity. So when we look at objects that are thrown horizontally, fired horizontally, rolled off of the top of a tall building, and was traveling horizontally, we say the moment it becomes freely falling, the moment it begins to fall downward in this parabolic path, at the very beginning, in this particular problem, we're going to say, yeah, it's got a significant sideways velocity. In this case, it was fired sideways at 7 meters per second. but its downward velocity, its vertical velocity at the beginning is 0. Wasn't thrown downward, it wasn't fired downward, or it wasn't fired upward. It was fired perfectly horizontally. So at the very beginning, its speed in the up-down direction, this portion of the velocity vector, is 0. And that's an important idea to have that at the beginning. This velocity, the vertical velocity, is 0. All right, let's look at one or two problems, and that'll be it for today. All right, so if we go to we're working on projectile motion now. Let's go to motion charts. All right, so here we have two quick problems. Okay, here we have a student fires a cannonball horizontally, perfectly horizontally, off the top of a tall building as shown. The ball remains in the air for 6 seconds. Fill in all the information. Okay, so it's fired perfectly horizontally. So the moment that the cannonball exits the cannon and is able to fall freely, it has a 30 meter per second sideways velocity. That's the x direction or horizontal direction. So that's what we fill in this column. Velocity in the x direction starts out at 30 meters per second. And what is its velocity in the beginning in the y direction? And the initial velocity in the y direction is 0. And whenever we do these projectile motion problems, we're only going to be considering the x direction or the y direction in any particular analysis. All right, so we know what's going on in the beginning. 30 meters per second in the horizontal direction, 0 meters per second in the vertical direction. What about acceleration? Well, we know acceleration in the up-down direction, in the y direction, is 9.8 meters per second squared. We're going to use 10 for an approximation here. But it's gravity. Gravity is accelerating us in the y direction, the up-down direction. In the x direction, there is no force. There is no gravity pulling objects sideways, pulling objects in the x direction, or pulling objects horizontally. And so we say the acceleration is 0. There is no force. There is nothing pulling objects horizontally. So the acceleration in the horizontal direction is 0. All right, so let's look at the speed in the y direction. We said it starts out at 0 in the y-axis because it came off with a perfectly x-axis speed. It came off with no speed in the y-axis to begin with. It had 0 meters per second of speed in the y-axis to begin with. But after 1 second, its gravity is pulling it down. So after 1 second, it's going to have some downward speed. What is that downward speed going to be? 10 meters per second. After 2 seconds of time in the air, what is the downward speed going to be? 20 meters per second. After 3 seconds, 30 meters per second. After 4 seconds, 40 meters per second. After 5 seconds, 50 meters per second. After 6 seconds, 60 meters per second. And that's all due to gravity. Gravity works in the y-axis, so gravity is going to change the speed of the object by 9.8 meters per second each second. And here we're approximating that as 10 meters per second each second. And so the speed just steadily increases. The y component of the speed steadily increases by about 10 each second. But what about the x-axis component of the speed? What about this horizontal speed? So we're neglecting air resistance, and in the absence of anything acting in the horizontal direction, its speed is not going to change at all. Right? We need a force to change the speed of an object. And in the absence of a force, the object will continue moving at a constant velocity. And so the sideways velocity, the x-axis velocity, the horizontal velocity stays constant the whole time. 30 meters per second to begin with, 30 meters per second, 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 30 meters per second. The whole time in the air, it is traveling. Its sideways velocity is 30 meters per second. Okay? When it was launched off the top of this building, what was its direction? It was perfectly to the right. It had no upward component, no downward component. It was right only. All right, next one. Same basic idea with the car. The sideways component of the velocity, the x-axis component of the velocity stays the same the whole time, 20, 20, 20, 20, 20. The y-axis component of the speed starts at 0, there's no upward downward speed to begin with, but as each second goes by, the y-axis speed increases. 0, 10, 20, 30, 40 meters per second of downward speed after 4 seconds. It still has that sideways speed the whole time, but that sideways speed hasn't changed at all. The x-axis speed has been constant the whole time. All right, let's do one more. Now this is our other problem. Just like we had two problems in free fall, where you drop something from a tall building or you kick something up in the air. Well, this is kind of the same thing as the kick something up in the air problem, except we're not kicking it straight up in the air anymore. We're kicking it at an angle. So let's say we kick an object or fire an object with a velocity of 22 meters per second at an angle. Well, if we can figure out, and there are ways to do this, figure out how much of that velocity is horizontal, sideways velocity, and how much of that is up and down velocity, or vertical velocity, or y-axis direction velocity, then we can perform our analysis. Remember, this velocity is going to be constant. Gravity doesn't affect horizontal velocity at all. This velocity is going to change by 10 meters per second each second due to gravity. Okay, so in this case, if we fire something that has an initial vertical velocity of 20 meters per second and an initial horizontal velocity of 8 meters per second, well, what's going to happen as it goes through the air? Well, first of all, we know it's going to take 2 seconds for all of this upward velocity to go away. So we're going to start off at 20 meters per second, right at time 0, right when it comes out of the cannon. Its upward velocity is 20 meters per second. A second later, it's going to be 10, and a second later, it's going to be 0. So that's going to be right here. At this location, our upward velocity is now 0. It still has a horizontal velocity of 8 meters per second, but the vertical velocity has decreased to 0. And then it begins to come down. So a second later, we'll be going at 10 meters. We'll have a downward component of velocity of 10 meters per second. And 2 seconds later, we'll have a downward component of velocity of 20 meters per second. So at 1 second later, we're now at 10 meters per second in the downward direction, then 20 meters per second in the downward direction. And this whole time that the object was going through the air, what was the sideways velocity doing? What was the x-axis or horizontal velocity doing? It stayed the same. It stayed constant. 8 meters per second, 8 meters per second, 8 meters per second, 8 meters per second, until it hit the ground and the object stopped. Okay? So again, the y-axis component of acceleration is gravity, 10 meters per second squared. The x-axis component of acceleration is 0. There is nothing causing the object to speed up or slow down in the x-axis. Okay? And this next problem is pretty much the same thing. Okay? You can see the horizontal velocity stays constant the whole time. The vertical velocity starts out at 50, goes 50, 40, 30, 20, 10, 0. So at 5 seconds, we've hit that highest point, and then 10, 20, 30, 40, 50 in the downward direction. All right, so hopefully that gives you a little bit of an idea. Let me show just one final quick video here. What we have is two objects that are being simultaneously, two balls up here, one's being pushed sideways, one's being dropped. And let's look at what happens. What we're looking at is how long do they take to reach the ground. And what you may have noticed is they hit the ground at exactly the same time, because they both had the same initial vertical velocity, which was 0, and they were both released from the same height. So they both traveled downward to the ground in an identical fashion. And you can see that at any moment in time there, they were both had the same height above the ground, right? Or from the launch position. So they both, whether they have a sideways velocity or not, they both travel to the ground at the same time, as long as their initial velocities were both in the vertical direction were both 0. Okay? So they both travel to the ground in an identical fashion. What's different is how far they travel sideways. This has no x-axis velocity to begin with, no horizontal velocity to begin with, and so it doesn't travel at all horizontally each second. This object does have some horizontal velocity, and so it travels one box to the right each interval of time. So as each little moment of time goes by, maybe it's a tenth of a second or so, it travels the same distance sideways because it's traveling at a constant velocity in the horizontal direction. So you'll notice each time another interval of time goes by, it travels another box to the right, and those boxes to the right are of a uniform, or those lengths to the right are of a uniform fashion. They're the same length. So as each moment in time goes by, it travels the same distance to the right because it's got a constant velocity in the x direction. All right, hopefully that helps, and we'll send more videos about this shortly. Thank you.